This is problem set number 5, problem 3. Two identical positive point charges, Q, are nailed down a distance 2d apart. In this diagram, point P is midway between the two charges. The dashed line is vertical and is perpendicular to an imaginary line connecting the two charges. What is the direction and magnitude to the electric force acting on a positive charge Q for part A placed at point P? Okay, so I have redrawn that here. Okay, so for part A, we have this positive charge Q, which is midway between the two charges, capital Q, and it's placed at point P. Okay? So right away, I can say that we are going to experience two forces, right? And the first force is pointing towards the positive x direction. That's FQ right here. And an equal and opposite FQ pointing towards negative x direction due to this Q charge, right? Due to this Q. That's a negative FQ force and the positive FQ force due to this point Q. Okay, so if our charges are going this way and this way at point P, then they're only going to be x component of forces, right? We're not going to have any y component of forces acting on at point P. Okay? So I will write down Coulomb's law for electrostatic force, and that is that the magnitude of electrostatic force is equal to K, electrostatic constant K, times the source charge, or Q1, times Q2, which is going to be the charge at the point that we want to know, the electrostatic force that acts upon it. And that's divided by r squared, which is the distance between center of charges, Q1 and Q2. By Q1 and Q2, I mean this Q1 and this Q2, okay? The source charge and the point where we want to find the electric force acting on that point. Okay. So let's do that. First, I'm gonna have I'm gonna go ahead and call this F1 and F2, okay? Even though they're equal and opposite forces, okay? F1 and F2. So first off, I know that I have no force acting along the y component, right? So Fy, that's going to be 0. I know that. How do I know that? That's because the positive charge Q at point P is midway between the two charges that are identical positive point capital Q charges. Okay, so no y component forces. What about x component? In the x component, I'm going to have F1, which is a positive facing towards positive x, right? And that's going to be subtracted by F2, which is facing towards negative x. Okay? And so they're going to cancel out because they're equal and opposite, but just in case you wanted to see that for yourself, so F1 would be K times the source charge, which is positive Q, right? And the magnitude of the little q, which is the point that we want to find the electroforce acting upon that point, divided by the distance between the center of charges, and that is d, right? That's this guy, d. And we subtract that by F2, which is also K for the electrostatic constant, times the charge for force 2. The source charge of that is also positive, capital Q. So Q, and then again, we're looking at the same point, which is Q. So that will be little q divided by, and the distance between F2's source charge and the Q is also D. So divided by D. And obviously these guys are equal but opposite in direction. So that tells us that delta Fx is also equal to 0. All right, so therefore, F total or the direction and magnitude of electric force acting on positive charge Q, if it's placed at point P, is 0. And that's our final answer for part A. All right. Now for part B, what is the direction and magnitude to the electric force acting on a positive charge Q if it's placed on the dashed line at a distance y above point P? So I drew that right here. So earlier, our Q was located right here, midpoint, along the same line, along the same horizontal line between the two positive Qs. However, now we are up here at a distance of y, still in this midpoint, but up a distance of y. Okay? So let's draw our forces acting on that. If this was, this is my x and this is my y, right? I'm going to have some, because these are both positive charges, I'm going to have a force going this way, right? And I'm going to call this F1. And also, these are also two positive charges, so I'm also going to have a force going this way. I'm going to call that F2. Okay. Notice this is a right triangle, right? Right here. So now let's look at our forces along x. Real quick, I'm going to call this angle theta. And they're going to be the same angle because this is the midpoint line. That dotted line is the midpoint, right? So I'm going to have components along for my F1 and F2, right? I'm going to have some F1x component here, and I'm going to have F1x. I'm going to have an F1y going up there. And then for F2, I'm going to have an F2x pointing this way, and an F2y also pointing up that way, right? Actually, I guess it'll be the same area where f1y is. So I'll also have an f2y going up, right? So I'm going to go ahead and break that down. f2x or f1x, what are my forces along x? I've got f1x pointing towards positive x direction, right? That's what I labeled as my positive x, is anything pointing towards the right of the screen. So I've got positive f1x minus, because f2x is pointing towards the left of the screen or towards negative x direction. So minus f2x. And they are, again, equal and opposite, right? f1x is f1 cosine theta minus f2 cosine theta, right? And we have established earlier that f1 and f2 are equal. The magnitude is equal, right? K times capital Q times baby q divided by d. Actually, that should be d squared. Okay. So anyways, f1 and f2 are equal, so f1 cosine theta minus f2 cosine theta, that's going to be equal to 0. So the summation of forces along x, that's going to be 0. They're equal. Due to symmetry, they cancel each other out. So that is my summation of forces along x. And summation of forces along y, that's going to be f1 sine theta plus, because this time f2, the y component of f2 is also pointing up towards positive y, so that's plus f2 sine theta, okay? And so f1, what is f1? Again, as we said, that's k times capital Q times little q divided by d squared. Right? That just comes from the electrostatic force equation in Coulomb's law. So that's plus, same thing for f2. It's also, sorry, I forgot sine theta. So this time sine theta plus f2 sine theta, which is, f2 is also k times the charge, source charge for f2, which is this now, right? Positive capital Q times little q, which is the charge of our point, divided by d2. No. This time, the distance between the charges is no longer d. Actually, this time the distance between charges here, so this is the hypotenuse of d and y, so the distance now here is going to be the square root of d squared plus y squared, right? So this is also the square root of d squared plus y squared. My apologies. So now the distance is the square root of d squared plus y squared, because it's no longer, initially we were here, right? Which was, yeah, that was just the distance between the center of charges was just d for part A. But now this is the distance between the two charges, which is the hypotenuse, or d squared plus y squared, because y is the height of, that's this distance right here. So d squared plus y squared. Square root of that. And don't forget the squared because it's r squared in the denominator. So this is also the square root of d squared plus y squared. Also sine theta. So that's a y component, right? Let's rewrite that. What is, actually instead of putting down sine theta, what is sine theta? Remember SOHCAHTOA. So sine of theta, which is this angle, the sine of theta is the opposite, which is y. So this times y over the hypotenuse, which is the square root of d squared plus y squared. Okay, and I'll also rewrite the sine theta as y over square root of d squared plus y squared. All right. So now if I add those two together, that is equal to 2k capital Q little q y divided by, that would be 2 over 2 plus 1/2. So that would be d squared plus y squared to the 3/2, right? Because x squared plus x to the 1/2 is equal to x to the 3/2, right? But instead of x, I have d squared plus y squared. Okay, so I've got that. And instead of k, I'm going to plug in k. Remember, the k is just equal to 1 over 4 pi epsilon naught. So k is the electrostatic constant, and epsilon naught over here is the permittivity of free space, or how well the electric field works in a vacuum. Okay, so I'm going to plug that in. So this is equal to 2 capital QQy over 4 pi epsilon naught times d squared plus y squared to the power of 3/2. Okay, and I'm going to simplify this even more. So I'll cancel out the 2 and the 4. So QQy over 2 pi epsilon naught d squared plus y squared to the power of 3/2. Okay, and that will be my sum of forces along y. All right, so therefore for part B, my sum of forces, or my F total, is going to be equal to the sum of forces along x plus the sum of forces along y. And again, as we mentioned, the sum of forces along my x component is 0, so that will be F total is equal to 0 I plus QQy divided by 2 pi epsilon naught times d squared plus y squared to the power of 3/2 along j hat, or along y. Okay, so this is my final answer for part B. Okay. All right, moving on to part C. Where on the dashed line should we place Q so that it experiences the biggest force? Okay, so now we're dealing with maximum force, right? So I want to know where on the dashed line to place Q for maximum force. So let's think of derivatives of functions again. Right? So let's say I was plotting a graph, right? And this was, let's call this y, and that's going to be the distance from the horizontal. Let's call this y, right? This axis is a y, and that's going to be the distance along the dashed line that I can place Q to experience the biggest force. And then let's call this my force line, right? And if I wanted to get the maximum force along y, right? Where would the maximum force be? If this was my force, then the maximum force would be somewhere here. That would be F max, right? Maximum force would be this point right here. What would be the derivative at my maximum force? That's where the slope turns from a positive slope, or yeah, here, a positive slope. It turns to a negative slope, right? But at this point right here at F max, my slope is flat, or my derivative is 0, in other words. When you have a flat slope, your derivative is 0, right? So I want to find where is my derivative, d over dy, actually, of my force, electrostatic force, equal to 0. That's where I want to find. That's where I would put my Q for maximum force. At this point where my derivative is 0. So I want to know where is this. Okay? And remember, the reason for that is because the derivative of a function describes the gradient or slope, right? I won't write it down, but I'll just say it real quick. The derivative of a function describes the gradient or slope. So when we want to find the maximum or the minimum even of a function, we want to find the point where the gradient or slope changes from a positive slope to a negative slope, or vice versa, right? In a maximum, we want to find where it changes from positive slope to negative slope. Okay? So that's the reason why I want to choose that the d over dy of f equals 0. So if 0 is equal to d over dy of f of my electrostatic force, right? What would be my electrostatic force? Again, what is electrostatic force? I wrote that down here. I'm going to bring it down so we see it again one more time. Copy, paste. Okay, that's my electrostatic force. So in this case, or actually I already solved it right here. That's my F total. Right? I just want to find out where y is. for me to have a slope of 0 or a derivative of force that's 0. So d over dy, and I'll plug in the value for my force, total force, which is qy over 2 pi epsilon naught times d squared plus y squared to the 3/2. Okay. And I'm gonna take my constants out. Which are my constants? Capital Q, little q, 2 pi epsilon naught. These are my constants. So I'm just gonna move it out of the derivative. So q over 2 pi epsilon naught times the derivative along y of y divided by d squared plus y squared to the power of 3 over 2. Okay? So I'm going to have to do a side mission just to get this part of the equation. So I'm going to do that right here, and I'll use a different color. Let's use, I guess, green for side mission. So side mission number 1. Or side quest number 1. I just want to find out the value for this. Okay. So I'm going to use the differentiation, the quotient rule, right? Which is d over dx of f over g of the function f over function g is equal to f prime times g minus g prime times f divided by g squared, right? And in this case, my f, or what I have in my numerator, is y, and g, which is what I have in my denominator, is d squared plus y squared to the power of 3 over 2, right? Okay, so my f prime, or the derivative of f, would be 1. And the derivative of g is going to be, I'm going to bring down the power, 3 over 2 times whatever I have inside, which is d squared plus y squared. And then to the power of 3 over 2 minus 2 over 2, which is going to be 1/2. And then chain rule, so I'll have to go inside. That will be the derivative of d squared. No, well, d squared will be 0 plus the derivative of y squared. Y squared would be 2y, and then times 1. Okay, so I'll just rewrite this g prime down, so my 2's cancel out, right? So then I will have g prime is going to be 3y times d squared plus y squared to the 1/2. Okay? So therefore, f prime g minus g prime f over g squared is going to be equal to, by the way, that's what this is, right? Okay, so that will be equal to f prime, that's 1, times g, which is d squared plus y squared. I need more space. Let me move this a little bit. So that's equal to f prime is 1 times d squared plus y squared to the power of 3/2 minus g prime, which is this, times f, which is y. So then that would be 3y squared, right? Let me make that a little bigger. Because I multiplied that by f, which is y, so the 3y becomes 3y squared. And then divided by g squared. And g is d squared plus y squared to the 3 halves. But if I bring that to the, if I square all that, then the 2's would cancel out, and I would just be left with d squared plus y squared to the power of 3. Okay? So that would be the derivative d over dy of this guy. So I'm going to plug that into our main problem. I'll go back to the main problem. So q over 2 pi epsilon naught times d over d, or sorry, no, I'm just going to plug this in now, times d squared plus y squared 3 halves to the power of 3 halves minus 3y squared times d squared plus y squared to the power of 1 half. Divide all that by d squared plus y squared to the power of 3, right? And I'm going to simplify this by getting rid of these constants. So I'm going to basically multiply both sides of the equation by the reciprocal of this. And remember, the other side is just 0, so I can multiply it by anything and it'll still be 0. So I'll write that down. So multiply both sides, or actually I'll just do it here. So I'm going to multiply both sides by the reciprocal, or multiply this by 2 pi epsilon naught over QQ. And since over here I also have a 0, I'm also going to multiply that by 2 pi epsilon naught over QQ, right? So clearly this will cancel out with this, and this will cancel out with this. And on the left side of my equation, anything multiplied by 0 is still 0. So then I would get 0 is equal to, and I'm just going to get this, right? So I just multiplied both sides by the reciprocal of this just to cancel that out, take out my constant, which I did here, all right? Awesome. So I'm going to split this into 2 terms. So d squared plus y squared to the power of 3 halves over d squared plus y squared to the power of 3 minus 3y squared d squared plus y squared to the power of 1 half, and divide that by d squared plus y squared to the power of 3, right? So I just used this, but I separated them into 2 terms, meaning this numerator with this denominator subtracted by this numerator and this denominator, right? Okay, so we're still good. Okay, so now, remember, this is still 0. So now I'm going to multiply again. This time I'm going to multiply this by, this I'm going to multiply by this term. I will multiply by 1, which I could do, right? So I'm going to multiply this by d squared plus y squared. This time to the power of minus 3 over 2 over also d squared plus y squared to the power of minus 3 over 2. So that's just 1, right? Because the numerator and denominator is the same. That's 1. I could do that. I'm also going to multiply the second term by 1, which is going to be d squared plus y squared to the minus 1/2 over d squared plus y squared also to the minus 1/2, right? And if you guys notice, all I'm doing is multiplying by the same term as the numerator with a reciprocal, or not the reciprocal, but the negative of whatever is in power. So 3 over 2, I'm going to multiply by minus 3 over 2 in the numerator and denominator. On the second term, I have to the d squared plus y squared to the power of 1/2. So I'm going to multiply by d squared plus y squared to the power of minus 1/2 in the numerator and denominator. So that's just multiplying them by 1, right? So if I do that, then these would cancel out, right? Because x, let's say x to the power of 3/2 times x to the power of, let's say, minus 3 over 2. That's just the same as saying x to the power of 3 over 2 minus 3 over 2. So then that would be x to the 0, which is going to be 1. Anything to the power of 0 is 1, right? So using that math wizardry, I could simplify this equation as, so this will still be 0, but this time it's going to be 1 over, and in the denominator, we've got to the power of 3, or let's call it to the power of 3 over 1. And then I've got to the power of 3, and then this one has to the power of minus 3 over 2. So if I add that, that would be like doing 3 over 1 minus 3 over 2. But instead of saying 3 over 1, I'm going to say 6 over 2, which is still the same as 3 over 1. So then that would equal to 4 over 2, or 2. No, sorry, that's not right. Three over 2, 6 over 2. One sec. So 3 over 1 minus 3 over 2. That will be 6 over 2 minus 3 over 2. So that will be 6 minus 3. That's still 3 over 2. Okay, yeah. So that will still be 3 over 2. So 1 over d squared plus y squared to the power of 3 over 2. Okay. Sorry, I got confused there. And then minus 3y squared, right? Because over here I've got to the 1/2 minus 1/2. So if I add that, that's just 0. So anything to the power of 0 is 1. So now I've just got 3y squared in the numerator divided by d squared plus y squared. So x3 times x minus 1/2. So that's x3 minus 1/2, or x, again, 6 over 2 minus 1/2, and that'd be x5 over 2. Okay, So then the denominator would be d squared plus y squared 5 over 2, okay? Yeah, you've got to really pay attention in this stuff because it's easy to make mistakes. Okay, so I'm going to multiply both sides of this equation now by d squared plus y squared to the power of 5 over 2. So this whole thing, I'm going to multiply by d squared plus y squared to the power of 5 over 2, right? So I'm also going to multiply this by the exact same thing. Which is going to be 0 still. So then I would have 0 is equal to, this one would be d squared plus y squared. Right now it's minus 3 over 2, and then I'll multiply it by 5 over 2. So then it would be plus 5 over 2 minus 3y squared times d squared plus y squared minus 5 over 2, right? Because it's in the denominator, therefore the negative sign. Same here. And then that would be plus 5 over 2. So then that becomes d squared plus y squared to the 2 over 2, or to the first power, minus 3y squared times d squared plus y squared to the 0th power. Okay, so, and this obviously is still 0, so 0 equals d squared plus y squared, right? Because it's just to the first power, right? So I could just forget that, and it's just d squared plus y squared minus 3y squared, and anything to the 0th power is just 1, so I don't need to write that down. We can just imagine this as times 1, which we don't need to write, right? We don't normally write times 1. Okay, so now I have this value as equal to 0. Oh, I have some like terms, so that becomes d squared minus 2y squared equals 0. Okay, so 2y squared is equal to d squared, and y squared is equal to 1/2 of d squared. So d squared over 2. So then y is equal to, if I square root both sides of the equation, I would have now y is equal to d over the square root of 2. Okay, and that would be my final answer, and that is where I would place charge Q to experience the biggest force on the dashed line at y is equal to d over square root of 2. All right, that was kind of a long problem.